Hi, I'm Roger Barga, General Manager for AWS Robotics. And welcome to the Cloud Robotics Summit keynote. I'm pleased to be here today with Brian Gerkey, CEO and founder of Open Robotics. We both want to welcome you for joining us today in this session. Together, Brian and I are going to talk about the future of robotics. I will be covering the role of cloud and cloud services, while Brian will be talking about the software that runs on the physical robot itself. Let's dive in. I would like to first talk about trends that we observed and that influenced our initial product roadmap, which you actually might find interesting. And then I'll transition over to the role of the cloud in the future of robotics. We take a very broad view of what a robot is. To us, it's something that senses, often with multiple sensors on the physical robot. It will do computation over the data coming off of those sensors, perhaps path planning, obstacle avoidance, navigation, and then take action in the physical world itself. This to us is the definition of a robot. Now, there are numerous examples of different robot types, varying in size, shape, and function. But if we look at industrial application, we really see three prominent types of robots: drones, robotic arms, and what we call ground mobility robots. These ground mobility robots, this is what's really interesting to us. And we're actually at an inflection point. The expected growth in the use of ground mobility robots is expected to increase by almost tenfold over the next 2 to 3 years. And this is a trend that's been going on for quite some time now. In fact, by 2023, it's estimated that mobile autonomous robots will emerge as the standard for logistics and fulfillment processes. And it's not just fulfillment. By 2030, we actually expect 70% of all mobile material will be autonomously moved by robotics. You might ask, what's driving this? Well, over the last 2 decades, we've actually seen the cost of labor increasing year over year. But at the same time, the cost to actually build a physical robot has been plummeting. A LiDAR, which 10, 15 years ago may have cost tens of thousands of dollars, can today be purchased for less than $1,000. And the algorithms to process data for navigating a robot are often now using just very inexpensive camera under $10. So the economics has been a huge driver for this. And indeed, as noted in Goldman Sachs in 2017, we hit an inflection point where the price of a small robot for moving material around was actually cheaper than any labor anywhere else in the world. So we've actually really met a crossing point where robots are actually cost effective and there's strong economic drivers for them. And indeed, there's a survey of enterprise companies, top 550 enterprise companies, asking them, what are your top 5 reasons for deploying or planning to deploy robots into your operations? And if you look at the top 3, it's to improve productivity of their employees, the efficiency of their operations. The second answer is to actually improve the product or improve the quality of their product using robots and automation. And finally, to increase the operational efficiency of their facilities in which they're operating through the use of robots. And you might ask, well, who are using mobile robots? Companies like Office Depot, JD, Flipkart, Ryder, FedEx. In fact, the better question is, who isn't using robots today to automate their business processes and the movement of material? But the surprising point is just how little penetration robots have today. If you look at the ground mobility example and look at the processes such as pallet conveying, moving materials from dock inside, loading units, shipping and receiving, and then look at the robot types you would find there: forklifts, tuggers, pallet movers. Just 2% of mobile robots are automated today. And that's why the upside potential is so great for the increased usage of mobile robots, as well as just the further automation in the enterprise for moving and fulfillment in warehouses. So today, we look at the history. In the past, we were manually moving materials around manually. Today, we see a blended model where humans, in concert with robots, are actually moving materials. If you look at the future and imagine when we go from 2% to 20% to 50, to perhaps 100% of robot automation, it's a very compelling future ahead of us. And again, the takeaways for this section: economics is a significant driver in the use and uptake of automation. Second is to improve worker productivity, offer customers new services, and increase operational capacity. And there's customer demand for new experiences. Indeed, if you just look at Amazon, where a few years ago it was a game changer to have packages delivered in 2 days. Now, working with robots, working in concert with humans, we're able to fill orders within a single day. And with the innovations in Prime Air, we could actually be delivering packages with hours. Customers want these new experiences that can be delivered through automation. Now I'd actually like to talk about the role of the cloud in the future of robotics. And I want to do this through examples of our customers and using AWS RoboMaker. AWS RoboMaker launched at reInvent in 2018, in November of 2018. And there's 3 capabilities that I'd like to highlight in my talk today. The first are cloud extensions for robots that make a secure connection from the robot to AWS cloud services so the processing can be offloaded from the robot to the cloud itself. Next, I'll talk about simulation as a service as offered by AWS RoboMaker. And then finally, talk about our fleet management capability offered by AWS RoboMaker. One of our customers, Leah, has built a walker robot for the elderly and disabled. Again, Leah senses, computes, and takes actions. She's a robot. She has 72 sensors, a very low-end CPU to keep the costs low, and it's built for the elderly and disabled to allow them to get around their house. Our customer, the Leah developers, wanted to be able to add a voice interface to Leah so that their customers could interact with Leah in a much more natural way. They wanted to do real-time monitoring of their patients, as well as live video streaming so that they could converse with the doctor or a loved one could actually converse with the user of Leah. And the challenges the team faced is they had very little expertise on cloud services or machine learning. They had limited local compute power on Leah itself because of the low-end CPU, and all that CPU was being used to keep the patient safe. And they had limited engineering resources to throw at this problem. We worked with them to integrate AWS RoboMaker cloud extensions into Leah, such as Amazon Lex that allows the user to talk to a robot, Amazon Poly, which will actually generate voice from data and turn to voice. So now you have bidirectional communication between the robot through these cloud services. Amazon Kinesis Video, which allows us to stream video off of a robot up to the cloud for processing or for storage. Amazon Recognition, which will actually do as a deep learning model that will actually recognize objects in the video feed coming from Leah. And finally, Amazon CloudWatch, where you can actually stream monitoring data and logs off the robot up to the cloud and build dashboards for monitoring the patient and their activity. Here's just a slight illustration of the implementation. Along the top, you can see our cloud extensions running on the robot itself, making a secure connection back to AWS services such as Amazon Lex, Amazon Poly, and Amazon Recognition. In the middle line, we see that we're actually using our fleet management to stream diagnostics data and logging from the robot up to the cloud for monitoring the use of the robot and the patient, as well as anytime a Leah developer wants to update the application, they can actually push a new version of their application onto Leah and update the application to keep it fresh. What our customer was able to do with this, they built a voice interface for Leah within hours of starting the project so that the patient could talk to the robot and the robot could in turn respond back to them with a voice, a natural voice. They were able to build live monitoring and alerting within days. They could actually monitor the activity of the patient using Leah. And they built live video streaming for Leah within days as well. Here we see a quote from our customer. But through the augmentation of the processing on the robot with AWS cloud services offered by AWS RoboMaker, these developers were able to significantly enhance what the robot was capable of doing without adding any cost to the actual physical robot itself. Let's turn to simulation. And simulation plays a myriad of roles in robotics, beginning with just being able to test an application out and see if all the messages are flowing, if the application is responding correctly to the sensor input. AWS RoboMaker offers simulation as a service. There's zero hardware and infrastructure for a user to provision and configure. We offer it. We scale it up automatically as the simulation gets more and more complex. We provide the necessary processing power for the simulation, and customers only pay as they go. And they're not limited to running just one simulation. They could actually run hundreds of parallel simulations to test their application under a range of conditions. In fact, we were approached by a customer, iRobot, and what they wanted improved test coverage for their robot for different floor layouts, different home scenarios of furniture placement, of debris along the floor, and different floor plans. And they needed to really improve the code coverage and the speed at which they could test their application and get that new application out to their customers as quickly as possible. The challenges they faced, that was very costly and time consuming for them to test their robot under all possible conditions because they had a fixed number of machines. They had limited test cases they could run in parallel. And as a result, it actually took weeks for them to actually test their application. And on occasion, bugs were actually getting injected into the code and not getting discovered until much, much later. And what they wanted was a large-scale automated testing framework using our simulation service. We worked with them to create dozens of simulated environments, different floor layouts, different home types, different configurations. And today, they have 40 automated tests that each time a developer attempts to check in code into a repository, these tests are run in simulation to verify the application's running correctly. Whenever the developers attempt to push a new update out to their customer's robot, they run 500 tests in simulation to verify the application is going to run correctly as desired. And they've actually been able to reduce their testing time down from 3 weeks down to 1 hour for one important test case that they're trying to protect against. So this is a significant game changer for them. And in fact, many of you who have been using AWS Deep Racer have actually been using RoboMaker simulation all along because there's another use for simulation as a service. And that is to actually use reinforcement learning and simulation to train a robot to perform manipulation and navigation tasks. In Deep Racer, we start up simulations of different track configurations, different track conditions, and an intelligent agent is actually attempting to drive the vehicle. Reinforcement learning is capturing all the mistakes that the vehicle makes, giving it positive and negative reinforcement. The machine learning algorithm improves the performance of the agent, effectively training it through simulation how to actually drive a car. And then we can actually use our fleet management to deploy that reinforcement learning agent to a physical vehicle where it is actually able to drive the car using that agent in the real world for the first time. Now, as you can see, this car is still in its learning process because teams who win Deep Racer events actually are able to go around this track in 6 seconds. So it still has a lot of learning left to go, but you're now seeing the application of simulation and reinforcement learning to program robots. So if you pan back and ask, what is the role of the cloud in the future of robotics? Well, we can see in the case of LEA, intelligent cloud services can enhance the local processing on the robot and improve the performance of a robot over time. We can use simulation, such as what iRobot has done, to test application correctness and ensure the performance across a wide range of conditions to ensure the robot's going to perform correctly in the physical world. And then finally, simulation combined with imitation and reinforcement learning can actually be used to program robot actuation and navigation. So now I'd like to turn it over to Brian Gerkey to discuss the development of software that runs on the physical robot itself.
Thanks, Roger. It's a real pleasure to be here and to be part of this Cloud Robotics Summit. So I'm going to tell you about the software tools that underlie the service that Amazon has put together with RoboMaker. They are namely ROS, the robot operating system, and Gazebo, robot simulation. These are both open source tools that we, together with our global community, have been developing and maintaining for well over a decade now. Now you might ask, why do we write robot-specific software? What's special about robots? Well, programming robots is, it has all the same challenges that any other software engineering endeavor does, but we also have to interact with the physical world. We need to use sensors to understand what's happening out in the world, build some kind of representation of what the state of the environment around the robot is, and then decide what the robot's going to do. And it turns out that structuring and debugging that software is a big part of the challenge in developing any useful robot application. The approach that we take with our software is we really want you to develop and test your software in simulation first. And so we provide in Gazebo, which you can see here, a simulation environment that reproduces the robot as well as this environment. And then you develop your software using ROS, which takes a distributed approach to robot programming. What we want you to do is to develop independent modules that interact with each other through well-defined interfaces that together produce the behavior that you want in the robot. So if you follow this development path, you can build all your code in using ROS, and then you can run it against a simulation of your robot in the environment that you want it to run in and prove to yourself that it works. Now, if you've done that carefully, then when it's time to go to the real robot, you can just use the same code. And so what I've shown you here is there was a simulation of NASA's Valkyrie or R5 humanoid robot. And it has actually been, it was the case during a competition that we ran where someone who developed an entire autonomy stack for this robot in simulation was able in the course of just a couple of days to transition that entire software stack to the physical robot and run it in just the same way. And this is really what we want to allow you to do using these tools. So let's dig a little deeper into each tool and then run through some use cases. So first of all, what is ROS? ROS stands for Robot Operating System, and despite the name, it's not an operating system. It's actually, you can think of it as an SDK or software development kit. It's a set of software libraries and tools that run on top of an operating system, often Linux, but also other OSs. And it gives you what you need to develop robot applications. So at the center of ROS is what we often call plumbing. We take a distributed approach to developing these systems, and so we need a way to connect together the different distributed components. And we could call that plumbing or middleware. It's a message passing system. We also provide developer tools. As I mentioned earlier, programming robots is hard. You need good tools to allow you to specify the system, to launch it, to introspect it, to find out what's happening, to debug it, to log data, to play it back, and to visualize data. And that's a key aspect of the ROS SDK. We also provide capabilities, which are implementations of algorithms that you as a robot application developer should really be able to take for granted. Many important problems have been well solved over the decades and from the robotics research community, whether they be mapping of indoor environments, navigation algorithms, perception algorithms. And to the extent that those are well understood and solve problems, we want to make sure that you have access to the best-in-class implementations of those algorithms. And so what ROS gives you are the algorithms that you can take off the shelf, you configure them, and then you can build them into your application. And then, of course, ROS is an open source project. And so there's a global ecosystem. And that brings with it a large community, hundreds of thousands of users and developers around the world who are relying on this software. They're available answering questions about it, and they're contributing to it, which of course I hope that you do as well. Our focus right now is on ROS 2. ROS has been around now for over a decade, and about 5 or 6 years ago, we started working on a major rewrite of ROS, which we call ROS 2. While ROS has seen significant use in production environments around the world, it's used 24/7 in a variety of different kinds of applications all over the world, we knew that there were opportunities to improve the software, in particular to make it more suitable for use in environments where some kind of verification, validation, or certification are required. We also thought that we could improve the system reliability and improve the fitness of ROS for environments that require real-time execution. Taking all those considerations we decided that the best way to achieve those goals was to do a rewrite of ROS from the ground up. And so that's what we've been doing for the last few years with ROS 2. It's a big effort, but fortunately we don't have to do it by ourselves. We have convened the ROS 2 Technical Steering Committee, which includes some of the largest companies in the world, as well as a number of other smaller organizations. And the key thing that each of these groups is doing is they are contributing their own in-house engineering efforts to the project. So all these organizations have their staff working on ROS2, making open source contributions to the project. And that's what is fundamentally driving it forward. Our status right now is that we put out our most recent release, which we codenamed Foxy Fitzroy, earlier this year in June. This is a long-term supported release, so you'll be able to use this with supported updates through May 2023. And our focus for the rest of this year, based on feedback from our technical steering committee and our broader community, is to make ROS2 even more suitable for those production environments. We are in particular going to focus on improving the out-of-the-box experience and also the documentation. Switching gears to Gazebo. So ROS is the software that you use to build your robot application, and that's what runs on your robot. But as I mentioned earlier, you can also run that in simulation. So you take the same software and you connect it to the Gazebo simulation of your robot instead of to your physical robot. So then what is Gazebo? Gazebo, there are many approaches to simulation, philosophical approaches. Our take on simulation is that we want Gazebo to be the best possible software stand-in for your physical robot. And that means that we want to capture all the physical aspects of the robot, its motors, its sensors, its physical body, as well as the environment in which it operates, whether that's a home or a factory or a city street. So we need to model that entire environment. And then what we do is largely simulate how physics unfolds in that environment. We do what's called rigid body dynamics. You can think of it kind of like a video game, but we're much more careful with the way that we do physics simulation. We also need to reproduce all those sensor inputs. So if your robot has cameras, lasers, IMUs, GPS, those are all common sensors you might put on a robot. We need to be able to synthetically generate those sensor inputs in the simulated environment to feed the same data that you would get on the real robot into those same algorithms. We also provide a graphical interface so that you can see what's happening in the world. We have interfaces so you can connect the simulation to other tools, ROS very commonly, but Gazebo can also be used with other message passing systems that are not ROS. And of course, we really want you to take advantage of cloud resources to be able to run as many simulations as possible, as fast as possible. Over the past few years, we have been taking Gazebo, which is actually a project that is almost 20 years old now, and breaking it up, kind of re-architecting it into a collection of libraries that we call Ignition. If you use our latest version of Gazebo, it's already making use of these libraries, and hopefully you can see the benefits of that when you use the latest version of the simulator. But I wanted to mention that these libraries exist because these are also artifacts that you might make use of in your own work. So if you have your own simulation technology, you might find some utility in these underlying libraries and be able to take those and build them into your applications. Our status right now on the simulation front is we've released the Ignition Citadel, came out in December 2020, and that will be around and supported by us for 4 years from its release date. And our focus for the rest of this year with Ignition is what we call closing the gap. So Gazebo, as I mentioned, has a almost 20-year history. Ignition is a newer re-architecting of the Gazebo libraries. And when you use the Ignition Gazebo simulator today, there's still some places where we need to fill in some feature gaps. So we're working hard on that. So how does all this stuff really get used? I'll show you a few use cases of projects that we've done. And I should say there are many, many more applications out there that our broader community has used. So what I'm showing you here is a project that we did together with NASA Johnson Space Center, in which we simulated that their Valkyrie humanoid robot. And here what that robot is doing is planetary habitat preparation in advance of a human mission to Mars. So what the robot is tasked with a number of jobs in order to get the habitat ready for humans to come. And this was set up as what's called an eyes-off teleoperation task, or supervised autonomy. So in this case, there's a human who can see through the sensors that the robot has, but with a significant lag, because of course this robot's supposed to be on Mars, and then is able to send commands to the robot to get it to do these tasks. So these tasks that you're seeing are not completely autonomous. They rather have a human in the loop, which is very common for robot applications. And this is the example where the winner of this simulation-based competition that we ran was able to take the code developed in Gazebo and make it run on the actual physical robot in the matter of just a couple of days. Another example is a project that we're currently doing together with DARPA. This is called the Subterranean Challenge, or SubT. This is another competition environment in which the competitors are programming robots to go into underground environments to do search and rescue tasks. In this case, we have not one complex robot, like in the case of the Valkyrie humanoid, but rather a large team of simpler robots. These are wheeled robots, also aerial vehicles, and sometimes legged vehicles. And in this case, what the teams need to do is to program these robots to run through these environments, searching for artifacts, such as they could be humans who need rescuing, they could be backpacks, and there are a number of other artifacts that are to be found. And here you can see some of the latest work that we've done in modeling large environments that are in low light conditions. So we've got vehicles carrying their own lights, and also the ability to do multi-robot simulation, which is important for a lot of applications, not just search and rescue. One last application that I'd like to show you is actually one that we worked on a couple of years ago, but that has now been taken on completely by our friends at NIST. And this is called ARIAC. This is a simulation-based competition to control robots in industrial environments with the particular goal of improving the agility of the robots. Not the physical agility of them, but rather the ability of the robots to respond to unforeseen circumstances. And it's quite common that robots are used in industrial settings these days, but they tend to have very little tolerance for unforeseen events. So if something that's unexpected happens, at best you would hope that the robot just stops. The goal of this competition is to have the robot be able to, on the fly, autonomously react to these unforeseen circumstances, whether that's it tried to pick up a part and the part dropped out of the gripper on the ground, or it delivered the part that was requested, but the QA system says the part was faulty and so you need to go get another one. These kinds of events are baked into this competition, and then the competitors have to write their application software to be able to autonomously control this robot and handle all of those unforeseen circumstances. So this is a nice example of how you can use all this software in an even different third domain. So I've shown you three very different application domains, but a common theme that runs throughout them in developing these simulation environments is that it's very labor intensive to develop all of the worlds. So whether it's a Martian environment, a factory, or an underground network of tunnels, it requires a lot of effort to build those environments and let them have all the detail that they need to be able to run robots through them and get useful test results. Even with good tools and talented artists, you just never have all the environments that you really want to have in order to do large-scale testing. And in the end, that's what we really want people to do with the simulation software, is to do the kind of large-scale testing that gives them the confidence that their applications are performing in the way that they want before they deploy them to hardware. So what we really need is automation that can help with that where we can specify approximately what we want in the environment, and then we can have automated generation of massive sets of environments that match those criteria that we can use for testing. And that's what Roger's going to tell you about now.
Thank you, Brian. As you just heard, creating a simulation world can cost tens of thousands of dollars and take countless hours away from a team just to create a single simulation world. We're pleased to announce today the availability of AWS RoboMaker WorldForge. WorldForge is a new capability of AWS RoboMaker that enables our customers to build a simulation world in minutes. Not just one simulation world, they can build tens, hundreds, or thousands of simulation worlds in minutes so they can test their application across a wide range of scenarios. We're initially launching WorldForge, focusing on indoor ground mobility robots operating in homes. But over time, we're going to expand WorldForge to other world types to create simulation worlds for other buildings and other facilities. Here, let's take a look at WorldForge.
Introducing AWS RoboMaker WorldForge, a new capability that makes robotic simulation easier. AWS WorldForge makes it faster, simpler, and less expensive to create a multitude of 3D virtual worlds to simulate your robots in. Robotic companies are building increasingly sophisticated robots with autonomous capabilities and artificial intelligence. To develop these capabilities, developer teams need simulation to test and train their robots. Scaling simulation unlocks the ability to make regression testing more robust, reinforcement learning faster, and synthetic data generation more affordable. Until today, it was difficult for robotics teams to do simulation because building even just one 3D world was costly, time-consuming, and required specialized skills in 3D modeling and knowledge of simulation engines. Given the investment needed to create a single simulation world, it was almost impossible to build enough worlds to effectively scale simulation. With WorldForge, robotics developers can easily increase the scale, speed, and variance of simulation, improving the quality of production code and accelerating time to market. In this demo, we'll show you how to create dozens of randomized, realistic simulation worlds automatically. Before you generate worlds, you define your environment template, which will be used to generate randomized simulation worlds. WorldForge makes it easy to customize the assets in your worlds and set variation parameters of your simulation worlds. Starting from a pre-made template, you define the number and type of rooms you want and specify the room's area and ratios. You can customize a room type, layout, and even say which rooms will be next to each other. Finally, in the room itself, you can choose custom floor materials, wall materials, and furniture types. After the template is defined, QA engineers and robotic developers can easily generate multiple randomized simulation worlds for different application testing and reinforcement learning scenarios. Now, I'll show you how easy it is to generate worlds. First, define the number of variations needed for the floor plan and the interior variations. Then, simply click Generate the new world and create. Look at that! We generated 50 worlds based on the parameters in the template. Notice that each world is a variation of the template. You can tag these worlds with metadata so that you can easily search for them later. For example, you could tag a world with 3BR for 3-bedroom, hardware floor, or even high-density furnishings. You can also use these worlds paired with RoboMaker's Batch API and highly scalable infrastructure to quickly and easily run large-scale simulation workloads. We're really excited to make it easier and faster for robot builders to create simulation worlds so they can do more testing, better testing, and bring their robots and features to market faster.
We are excited about how WorldForge will help our customers improve the robotics application testing and machine learning capabilities through simulation. In the session following this one, you'll hear from Ray Zhu, lead product manager of AWS Robotics, and Sam Gundry, the lead engineer of WorldForge, and they'll go into more detail into WorldForge's capabilities and show you how it works. We want to thank everyone for joining us here today. And we can now start the live Q&A.